Yeah, it's time for our next speaker, and it's Kartik. How do you say your last name? Pandya? That's pretty close. And he's talking about enterprise apps as 12-factor apps. Is it 12-factor app? Did I got that right? I'm going to let him talk about it. I don't know. Give a big round of applause for Kartik, everybody.
Can you hear me? Yeah, I can hear myself. So, all right. My name is Kartik. I work for a company called Manhattan Associates up in Marietta, or it's kind of Atlanta, in our corporate city, up about 14 miles from here. And I'm going to talk about how to make an enterprise app that's a 12-factor app. And we'll talk about what an enterprise app is, or at least my view on that, and what a 12-factor app is, and how to sort of combine the two to be able to achieve something like that. So just a quick thing about myself. I work as a senior director, cloud platform architect for Manhattan for about last 12 years. Before that, I was up in Boston working for a company called Iona Technologies. Worked as a Corba developer, and I did my master's from UMass Boston about 50 years ago. And I worked in distributed software. So I've been working with distributed software pretty much since about 97, 98 timeframe. And I've loved that space, and it has given me great pleasure to make systems connect. Now today we are talking about systems disconnect and then connecting back. So it's a nice turn of events over the last 16, 18 years, and I think I'll do my part to sort of go through what we could do to achieve that. All right, so let's start with 12 factors. There's a very nice short article, most of you must have read it. It's called 12factor.net, or the 12-factor app, which is essentially a very simple premise that says this is a methodology for building a modern software as a solution, software as a service solution. If you think about it, the principles here, and I'll talk about each one of them, also applies to any modern software, not just a software as a service solution. And I'd like to take it to an enterprise app as well as we go further. So there are there are 12 different factors. I don't want to go into the details of each one of them, but I'll talk about some of the very key ones here. Dependencies is, as it comes out, as the first and probably the most important of the 12 factors that I think. And what it means is it's actually lack thereof, or dependencies that are explicitly mentioned in a sense where a developer, a particular part of the system, as well as the operator of the system knows exactly that part of the system and its dependencies, if there are any. Instead of a typical system or a classic legacy application where applications inside the code sort of depend on any other module, anything that is public that you can use, that kind of an approach, right? So here we are talking about dependencies as a very clear-cut separation and definition. Configuration. Every application requires configuration. Configuration is scattered across all kinds of things, right? It's in property files, it's in relational databases, it's in flat files and YAML files and all kinds of stuff that you can think of. So we'll talk about how to manage that part as well. Backing services, which is essentially anything that you depend on. Any of your, whether it's a database, whether it's a search service, all of these are essentially your backing services. We'll go into a little bit depth of that as well. Concurrency and disposability kind of work hand in hand. How a system essentially works in a more of a horizontally scaled model as a concurrent system while being portable and disposable, where you can start and stop quickly and then have no state and be a quick launch, graceful shutdown, things like that. And finally, the dev-prod parity, which is essentially it says that try to keep your environments all the way from development to your production or operation environment as similar as possible. Now, some of this might not always work, and that's why it's guidelines and not really rules or mandates by any means. But that's essentially what we are going to base our theory on. So let's also talk about an enterprise app. A completely separate discussion. What is an enterprise app and what it must be? So enterprise app, first of all, has to be upgradable with zero downtime, right? I mean, we all know how much time it takes for a typical enterprise app for an upgrade cycle, 3 months, 6 months, sometimes a year in many cases. How do we make sure that it's quick and zero downtime? It has to be scalable, millions of lines of orders for a shipping system. It won't work if it's not scalable. It has to be able to deliver changes quickly, whether it's bug fixes, whether it's new enhancements, whether it's any sort of new changes. It can't take forever to deliver those changes. And it has to be manageable with a low OpEx and deployable with low CapEx. And I'll talk about how cloud sort of fits into this whole journey as well. So that's an enterprise app. We all know what it must be. And by the way, by enterprise apps, I typically mean the applications that are used for businesses, for whether it's a CRM system, supply chain systems, ERP systems, things that we typically think of as big, heavyweight, multi-million-dollar license, multi-million-dollar services implementation type of systems. So how many enterprise apps do we know that sort of match the 12-factor app guidelines or principles? I couldn't think of that many. Yeah, there might be one or two. Somebody could say Salesforce is one of them, but then again, Salesforce is not your true enterprise app. It's like sort of a platform to build an enterprise app. But I couldn't really think of many here. So I wondered why is that the case? Why something that is, said that helps you deliver changes quickly and upgradable and deployable and all that is not being used in case of an enterprise app? And what do we do about that? So some of the quick reasons, and by the way, I come from a company that went through the same exercise. We built these enterprise apps, supply chain software primarily, and we went through the same cycle. So these are some of the things that probably might have come from our own staff. So some of those good ones, like new functionality trumps architecture. A product manager comes in and says, nope, we are doing 3 new functionalities. You're not going to worry about architectural improvement this time. Or we don't have resources, or we don't know how to do it, what to do. And lastly, it's like, if it's not broken, why fix it? So these are all different reasons. You can call them excuses, whatever the word that you like, but that's what happens when it comes to thinking why these are not 12-factor apps. At the same time, if you don't do anything about it, if you just let it sleep in, then these are the things that could happen. And this is, by the way, based on experience, not just coming out from thin air. We have gone through this thing. We actually take 6 months to deliver, to build something, 6 months to actually finally release it, and it takes about an 18-month cycle for a new function to finally reach in the customer's hand, or not being able to scale anymore. JVM reached 64 GB of heap space. I can't scale vertically anymore. I have to be able to scale horizontal, otherwise I won't be able to do much with my, much to my load. Upgrades are costing more than implementation. Sometimes more, sometimes as much as an implementation. And the worst part is the customer knows about it, right? And when customer knows and says, hey, we paid you the license fee the first time, now you are upgrading and you are charging me in services implementation more money or same amount of money that you charged us before. How does that work? Usually upgrade should be smooth and no cost, right? And then finally the cloud. Obviously today's world, if you can't deploy on cloud, you are essentially looked at as on-prem only. Yeah, we'll move on. Right? That happens, right, to many of us. So all of these, when we think about this, it's not easy to go and convince your bosses up in Chicago that we want to do this. We want to make our system more a 12-factor, and we want to do the refactoring, make sure that architecture is modern. It takes a lot of work. In fact, for us, it took 2 years to convince them for a 1-year project. So that's exactly what happened, and that's going to be one of the tougher part for anyone to be able to do than rather than actually doing things. So doing things is also not that easy, but it's not as hard as convincing people that this is the right thing to do. So I'm going to leave all of you to fight your own battle. If you ever need this, I can't help you there. But if you do get convinced, then do 12 factors. That would be my personal suggestion, personal experience, and it has worked for us. So if you ultimately end up having that budget and having those resources and having the skill set, do prefer skill set like this most wonderful man up here. So what are the 4 main elements of going about this. Let's say you have an enterprise app, you finally convince everyone that we need to do this, and then you go about that. You start your project, a 2-year journey or 1.5-year journey to make your, say, CRM system into a 12-factor app. So again, an opinion here, it could be done 5 ways from the Sunday, but one of the ways that I like is to start with these 4 must-sees. And the first one in that is componentization. Now, I am not using the word microservices in my presentation pretty much anywhere. And the reason I'm not using it is microservices, although I love it, it conveys the wrong meaning. It conveys the meaning, it loses focus on service and gives focus on the micro. And when we say micro, it becomes very small in our mind, which is not necessarily true. People say small, people say 100 lines, 200 lines, 1,000 lines, what is small? 1 MB, 2 MB, 1 GB. Micro, to me, it actually means how much work does it do? What are the responsibilities of that particular piece of code or module? It's micro by the nature, not by the size necessarily, right? So because of that confusion, I use the word component, maybe a little bit vague, little bit more generic, but let's stick to the word component, and it also becomes my C rather than a microservice. Right? So I like the word component that way as well. So componentization is going to be one of the key things where, as Jeff said, you try to break the problem into smaller problems and then try to deal with each one of them separately. And with a specialized set of people who know how to do it, and then put the system back together to do what it originally did. The second thing you could do is containerization. And this is where we'll talk about Docker. There are other ways of containerization as well, but I like Docker. I think most of you do as well. So we'll talk about Docker, how Docker helps in this journey as well, and what it provides when it comes to making your components run in a system more as containers. Continuous integration is the next part. Some people call it continuous integration, some call it CI and CD, as in continuous delivery as well. I just like simple word continuous integration, where you are essentially creating a big feedback loop from all the way from the development to your operations and everything in between, and make that loop go faster so that you can get the feedback quicker into your development and you can fix the bug. For example, you find a bug in, say, your QA phase. You could very quickly find that out that, okay, this is a bug, I need to fix it. And you can write a test for that bug as well, so that the next time it doesn't bleed into QA and then go back to development. You can do the same thing for production as well. So we'll talk about the loop as we go in detail. And finally, the cloud awareness. I was trying hard to find the last C here, so I just, I knew what I wanted to put, but I couldn't find the word. So cloud awareness, and this is something helped us in a sense that when we started, we did not necessarily start with the mind of necessarily putting it on a cloud. We started with the mind of microservices and all that, but then we said, okay, if we don't design upfront to make it suitable for cloud, make it friendly to the different type of cloud systems, we won't be able to do it at the end. And the other thing that in an enterprise or a product company like Manhattan's case, we can't dictate what cloud the customer must use. We can't say go use AWS or go use Google. The customers have existing partnerships. So you might have a customer like Toys R Us, and they might not necessarily want to go with your choice of cloud. They say we are good with Microsoft, we'll go with Azure. So we need to be able to support not all, but at least the 3 or 4 major cloud providers, right? So having that mindset ahead of time also helps. So it's like a quick recipe. You all know, very quickly what needs to be done. It's not that easy, but it's also not that difficult, right? At least, that's what I can convey. So I'll try to list out 12 steps to move to a 12-factor app. If you have an enterprise app, what do you do in 12 steps to sort of reach to that stage where at least you are comfortable enough in building something? So we talk about componentization to begin with. Not a monolith, think in terms of components. So again, every time when we think of a system, don't think of it as a CRM system or your supplier management system, but rather think of things like receiving, and think about things like servicing a customer, and your inventory management, and your things like that, in smaller parts. or something called functional groups. So again, as I said, I don't want to make my services too micro either, because otherwise I would just end up managing 1,000 of them, which in itself is a problem. So I would go with something slightly bigger than micro, so you can call it milli or centi or something like that. But at the same time, keep the responsibilities to minimum, if not single responsibility. So the way we project is, we divide the whole system into functional groups. And when we say functional group, they are like closely related functionalities, the business functionalities that go together. So for example, your inventory management might be a collection of 2 or 3 things, which is inventory sync process. You might have an inventory lookup process or search process, few of those that all go into a single collection of functional groups. What's important though is you keep your code segregated into separate code repositories for each one of these functional groups. You can go even further than that, but at least one for the functional group. And here I've just given an example of, my code sits in one, DB sits in one, my configuration sits in the other. That's just a personal choice how I like to do it. You could slice and dice it in a couple different ways if you like. And the same way you would have another functional group called receiving, where you receive the shipment and load your stuff in the warehouse. That could be your second functional group. When you go and build this thing, you build a component artifact, you put it in somewhere in like Artifactory or Docker Hub or whatever it is, whatever that artifact that you build, along with its DB schema, and then finally run that as a component. And same way you would have the other one as well going, and they would talk to each other via API calls. So this is at a high level how functional groups can get converted into your components, if you will, where the components are completely separate from each other in the technical aspects, but they work together when it comes to the logical aspect or the functional aspect of the system. So the second step is to have a process model built in. So we talked about not having a monolith. One of the key problems with monolith is it's a single process. Right? If you are building a Java-based application, which we do, you're going to build a single JVM that has a large heap size and all that. So we are talking about process model here, where we break each of these components into separate processes. So this is one of your components, and we use Spring Boot, so I just put an example of that with Spring Boot and Jetty or whatever that you have, your REST services, maybe even the UIs. That runs as a single. So think of this as my inventory process that runs as a separate Unix process. It could be Dockerized, non-Dockerized, but it's a separate process by itself. And then it can have a dependency on another component, a wire dependency or a REST invocation dependency, as I explained earlier. You can have an external service, like a payment service that you are using from CyberSource, or you are using PayPal or something like that. That's also an external service for that matter. A database is an external service as well. And all of these are treated as separate Unix processes, or processes in general. And these are called backing services. We talked about backing service in the 12-factor app introduction as well. So this is how my system looks like from probably 50,000 feet altitude, and my backing services and different processes. How do I intercommunicate between these processes? These are all starting on ephemeral ports and host names. I have no idea where those services start. I can't have those hard-coded in my system as well, right? So I need to use some sort of a service discovery to get to the place where I can communicate between the two. So you have two components talking to each other. We use Eureka. There are other ways of doing the service discovery as well. Essentially, it goes by you register. The first component registers itself. The second component finds itself, and then they talk to each other. And this is a very simplistic view, but if you think it's actually very simple architecture in general, where you are essentially saying start everything on an ephemeral host and port, just register yourself when you start so that others can look you up. And then if you want to do scaling, you would use something called client-side load balancing rather than using a server-side load balancer, where you say, I want to scale my component A 4, 5, 10, a dozen times. Sure, go ahead, do that. Each of them are going to register in Eureka, and I have something called Ribbon or any other client-side load balancing library that I could use on my client that would say, I will choose between one of these 4 instances of component A rather than somebody else choosing it for me. So that's how your client-side load balancing can be worked. And obviously, Eureka being stateless, you can, any service discovery being stateless, you can cluster it to 2 or 3 times. And you have to sync the data that it has, but you can always do that as well for better performance, obviously. Externalizing the configuration is the third step in the process, where you want to make sure that you don't end up putting your configuration inside your code, but rather have that externalized into a different source. So I have a config server, which is, has a version control information. So my properties file or YAML file reside in a version control system. I read it in my config server. I put that in a NoSQL database like Redis or console or something like that. And then finally I read it from my application. So when my application actually reads it, or my component actually reads it, it doesn't really care where it came from, who managed it, who changed it, all that. But there is a separate system that version control it for tracking and auditing and other purposes. So what you are saying is you're putting your entire configuration, instead of floating file system or in database or things like that, where you have no control as to what and who changed, you are actually putting it in the in Git and reading it from Git. We all talk about backward compatibility all the time, right? Especially when we talk in terms of API. But how many of us actually take it seriously? Like seriously as in, do not change backward compatibility. There is no version. There is nothing. Once you put a system in, once you make it production ready, you are logged in with that contract. It's like, a major league baseball player for like 10-year, $241 million. You are logged in. Now, obviously there are ways to change it and make it, you can trade and things like that. But as a general rule, you have to be very serious about backward compatibility for your upgrades, for your extensibility. All of those stories will fall apart if you don't do this. So what essentially this means is, in the version 1.0, very first version, I had 3 services in my inventory object that said, look up, sync, and update. In my version 1.x, I said, okay, I need to add a new method called add, and I need to change the method called sync to sync prime or sync 2. I can't remove my sync method right there because it's version 1.1. There will be people who are dependent on that. So I'm actually deprecating it. So this is where you can use the deprecation model very effectively as well. And then maybe version 2 or 3 at some point when you say all of the customers, all of the clients that are using this service are no longer using my original sync method, I remove that method and make it to sync 2. So you have to give that time. You have to make sure that the customers have completely gotten rid of that references before you can move that. Making your component disposable is also one of the key things when it comes to making your system 12-factor compliant. Essentially, disposability means 2 things. One is that you don't keep any state, so that every instance of the component that comes up works exactly like the other one. And the second thing is the component doesn't know how many other instances are running in the system either. So I'm not dependent on something already running, my own instance, or something that would be running behind me when I'm gone. So I run as a single self-centered component, nothing else around me. I just care about myself. And the second part of the story is also that it's also equally important to have a very quick and graceful shutdown and startup. You cannot leave things like JMS messages behind, or you cannot leave things like somebody else will clean up my memory and things like that. You have to do all that work when you shut down. When you start also, you need to start up quickly and then maybe lazy load things. That way you can start serving as soon as possible. So this is a request coming to a component, or one of the instances to the component. And where you are under load, the other instances automatically start coming based on your scaling rules, which we'll talk about a little bit later. And they can also go down when the load collapses. You just created more instances and shrunk back in when you did not need it. This could only happen if your system was completely disposable. Next, we talk about containerize as our 6th step. Essentially, containerization says that you take your component, encapsulate it with your technology tech stack and other switches that you are putting, burn that into an image, and use that image for every other deploy that you want to do after that at a very high level. So you have a component, you have a containerized component where you have the technology stack. In this case, it might be Ubuntu, Java, probably some other things as well, along with its configuration. And then you are putting it inside an image. And then now that you have a single container, you can run on a boot to Docker on a Mac, like the way I run here, or you could run it on an RHEL VM. Just, the customer says, I want to have all deployments on-prem. You can just run the Docker container on RHEL directly, or you could run it on an EC2 a VM as well up on the cloud. So this is what also provides you the deployment abstraction, if you will, where your container essentially takes care of making sure that the entire technology stack and its dependencies are sort of buried there, so you don't have to worry about doing separate installations and different configurations for each of your target target environments. Which also goes back to the point of do not let your deployment configuration of pieces bleed into your code. And by that, what I mean is essentially when you are running any of these components, at that level, the platform should be completely out of transparent. The Docker containers themselves should have no awareness, or the component inside it, about the platform that they are going to run on. This means don't have your AWS SDK references inside your code, don't have references to any other cloud pieces, don't have hard-coded, if you say I'm using RDS in my code, then you are stuck with RDS. You cannot use something else, right? So don't use that kind of references. Use environment injection. So Spring, in cases of Java, provides a very nice injection mechanism where you can configure properties. Other languages also have similar mechanisms. You can use environment variables. Like for example, if you want to run the same container on PWS, or Pivotal Web Services, you take the container, put it in, you set up a configuration environment in your space. So whenever this runs, it automatically gets those configuration environments that you put in, as well as other system things like vCap services and all that. So depend on your environment variables and your externalized configuration, rather than putting that hard-coded in your code or in your scripts inside the container. So decoupling is equally important, so that you can achieve something like this, where your containers don't really care where they are running on. They could be running on any one of these different ways or other ways that could be possible without really caring about where they are running physically. So this is just a sort of putting the pieces together. I'm not going to go too much deep into this. Using log aggregator is one of the benefits that we have achieved as well, where we use an external log aggregator like a Logstash to collect all the logs from all the different containers that are running in the system, and putting that in a central place where we can search and view using a good little UI tooling. So at a very high level, the way it works is your component essentially do a standard out. They don't care about where they are logging. They are not logging to a file system. They are not waiting for I/O. There's no performance bottleneck that way. They are just simply dumping it on standard out. And something like Logspout, which is what we use, that reads that output, puts it in Logstash. It's just as an event stream, which gets stored in Elasticsearch, and then finally viewed from Kibana as a UI. Or you could write your own UI, or you can have a UI in your application that reads from Elasticsearch as well. So this makes it very easy, especially in a componentized world where all the components are scattered. They are all running together in a single collective system. But if you think about it, a user's activity, a user says, I want to update something, it goes through a bunch of different components, that particular transaction. So how do we make sure the logs of all of those components are available at a single place? If you had all of them in file system, you'd be searching through different log files and matching the timestamps to see where the logs are. This would really help. You could say this particular transaction, and it would show you all the logs for that particular transaction. You can obviously scale your Elasticsearch and Logstash as well. The step number 9 is about having continuous integration in place. We talked about continuous integration earlier as well. We use these 6 steps that we consider as part of the continuous integration, from development, from integration to QA to simulated prod environment to user acceptance, and finally in production. And we run different types of tests for each of these. We use JUnit for testing. You could use other technologies as well. But JUnit, the way, all of these test cases essentially are JUnit test cases. We have created our own annotations that says this is an integration test versus this is a performance test versus this is a functional automation test, so that we only run those tests on that particular environment and not in a before or after environment. And we keep doing this on a daily basis, this whole flow from left to right. You can decide if you want to do it every day, every week, every month, whatever the frequency that works the best for you guys. This also acts as a quality gateway, or I call it bottleneck by design. So essentially, you don't let anything go out of the system unless it's tested. It's like a gate. So no matter how many developers, no matter how many components, but if it doesn't go through that funnel of testing, you can do this. So what we have, we actually use Artifactory online for our Docker image repository. So what we do is, for each of these levels, as we go further, we promote that particular Docker version. So if we have an inventory Docker piece, where we start, we call it iron. We just, for a lack of a better word, we said iron, bronze, silver, and gold would be our promotion designations. So at each level, we say, okay, integration always pulls iron images, and once it passes, it makes it a bronze image. The same image, it just tags it as bronze. And that way we can continue producing the different tags all the way into production. So production always knows that I'm only supposed to take the images that are tagged prod. Or QA always knows that I'm only supposed to take bronze images, nothing else in the system. So a system, no matter how much a code works or doesn't work on your computer, if it's not bronze, it doesn't go to QA. So this sort of locks it down and creates a strict gateway into the system. We also do the testing of each component in isolation. What it means is, don't try to test the entire system all the time, because there are too many variables. So you do instead of doing the entire system, you do something like this, where you say, I'm going to test my inventory component, for example. All of its dependencies, I'm going to get the stable ones, or the gold ones, if you will, the gold from my previous step. And then I'm going to put this new component that I did, or the iron component that I just now did, and test it against all the other stable ones. So I only have one variable. Anything breaks in the system, it's because of the new component. I know that for a fact. And here I only run the test for the new component. I don't run it for the whole system. So, and then finally you have an upgrade runway concept, where you are essentially, all the different component streams, the different developers, different pizza teams, if you will, they all come together and say, you develop all in parallel, but when we have to upgrade, we are going to create a single runway. Only after one component goes in, fits in, runs its tests, successfully completes its upgrade, we'll push the next one in. So this is also, creates another bottleneck, which is good, because that way we can control what goes inside your production system. Using a container management, something like ECS or Kubernetes is always, the right choice, rather than you writing your own Docker Compose-based logic and trying to run the whole thing. So, when you use container management, and I'm giving an example of ECS here, so it essentially creates a cluster. Kubernetes has similar terms as well, minions, if they, as they call it. But in ECS clusters, you have different instances that it creates, and they are all part of your bigger picture. These are different VMs that it would run the load on. When you run a service, let's say you say, okay, my service is inventory service, and I want to run X instances of an inventory task across these 3 or 4 VMs on this cluster. So it's going to start the task this way. When the load goes up, you can have the auto-scaling rules that says, create a couple more instances on these instances, start a new instance, and start a new task on that as well. So this is all handled by your container management, rather than you having to decide which VM to put your load on, which is the right slot based on the memory or CPU allocation, what should be the lower and higher threshold of your number of containers and all that. So that way you can actually control without having to write all that pieces of logic. So use container management if you want to run this thing more effectively. And my last point is something called pets versus cattle. And I don't know whether other people use it or not, but we started using it very routinely. Where for pets, for us, is all the essential services that you use in the system, which are known, right? I mean, you have a dog, a cat, probably horse, and you have names for them. They are there forever, or until they die at least. And you know them very well. And then you have a bunch of cattle that, some farmers even have names for their cows, each one of them. But in general, cattle are, like they come and go, if you think about it, right? Tomorrow you might buy 6 more cows or 3 more buffaloes or whatever it is. So that's the pet versus cattle. So your pets in this case are essentially your services that you use, messaging providers and Redis and database and, cache service and Elasticsearch and the whole 9 yards. And then your kettle, essentially the workload or your actual task that you are going to execute, that are going to be your actual functional components. And the difference between the two is typically your pets are going to be fewer. They are on the known locations. They are your essential services, so they need to be up before your rest of the workload starts. Kettle, on the other hand, could be many. You could start many instances of inventory system or many instances of your UIs to support the load. They start on ephemeral ports, so that's why they need the service discovery if you think about it. So that's how you, if you decide in your design what's your petal versus your cat, pets versus your kettle, it becomes much easier for you to set up the whole system, your infrastructure that way, with that mindset, right? So try to distinguish this. And as my, essentially my last slide, sort of putting the whole thing together in case of AWS where we run this, where we have, two availability zones that we created through CloudFormation. We created an Elastic server with Zool, our dynamic proxy for our components. Then we have two auto-scaling groups where we have the Elastic load balancers for each one of them, where we run all of our pets, if you will. And they are on the known locations. So as long as you know the Elastic load balancer's location, you know where every one of these components is, or every one of these services is. And then finally, you have the Redis, RDS-based service endpoint where we have component schema for all of the components that we are going to deploy. And the ECS cluster, which essentially runs our the workload, the actual workload when we start based on the couple slides ago. So the request essentially flows from my Elastic load balancer to my Zool server to my components, which would go need talk to Eureka or Logstash or any of those. They will also talk to Redis for obvious, keep saying Redis, RDS for my database support, and for other things as well, like for my monitoring and few other things. So this is, I sort of tried to put a picture together as, finally if you did that, now you have your system that is, upgradable with zero downtime, and this is where you could actually, it's scalable. Obviously, as you can see, it's also low cost because you are using AWS or some sort of a cloud and using the VMs and resources based on demand rather than pre-buying all of them as part of your capital expenditure. So that's pretty much what I had. I tried to fit in a lot of content in a small slide, but do let me know if you have any questions or anything. This is my email address. It was nice talking to all of you. Thank you. Do I have a minute or two for questions? I can't see anyone up there, but.
Oh, I see one.
Yeah, so please.
Great presentation. I have 2 questions and a comment. One comment is, I get the 4 C's and all, but I think like componentization is just one piece of microservices. And so I think you lose a lot of opportunity over the last 3 or 4 years of a lot of the IP and domain knowledge that we have, including the inheritance of things like Eric Evans, domain-driven design. And so again, that was my only little comment. Sure. The first question was, I noticed in that one step, like step 4, backup, you didn't mention anything about like some of the web scale practices like dark deploys or feature flags, and I'm sure are aware of those. Yeah. So did you not mention them because you don't think they're appropriate in the enterprise, or it just didn't fit the presentation?
No, actually it was there in one of the presentations. It just it just too much content to fit in, I guess, my 30-minute slot. So one of the slides that I took out last night was talking about essentially a Zool server, one of the edge servers that we use, and how the component masking can be used for doing dark deploys as well as behind the scenes changing your switches. So you are today using this component, tomorrow you say, okay, I want to change the API references or I want to change something else. You can switch that without the end user being affected because you are protecting them by an edge server that regard. Or you can put something new in, as long as you don't have the configuration for that, it's not publicly available, but internally you can test it and achieve your dark deploys as well that way. So I just didn't have that slide in the place. I mean, it might be better if you do it.
I just didn't hear anything about configuration management as a whole. How long does it take to spin up that Zool service underneath the top load balancer?
Very good question. And again, one of the other things that I had to chop off because of the time constraint. But we primarily have used two things mostly, AWS and Azure. Mostly AWS for the last about 8 months or so. And we have done a lot of work around cloud formation using AWS and along with Boto 3 as well. So with those two tooling with Python libraries that you have available, you can actually have the entire cloud formation that you have in your system version controlled as JSON templates. So I could have showed it to you, but it's a pretty big template if you think about it for the whole thing. But that you can version control, and that becomes your configuration for going forward as well.
That might make a good topic for an open space this afternoon.
Yes.
Let's give it up for Kartik one more time.
Thank you.
Excellent presentation. I really enjoyed that.
Thank you.